Okay, let's dive right into this explainer. I want to start by grounding us in a specific mindset, which is perfectly captured by the idea that security isn't some separate, isolated concern. It's actually an essential part of professional software development. It's an emergent property of literally thousands of small decisions we make every single day as developers. Think about it. When you build systems that communicate with each other, store sensitive data, or make decisions on behalf of your users, every single one of those activities carries implicit trust assumptions. We are not here today to look at security as an afterthought. It's not just a compliance checklist handed down by some completely separate security team right before launch. Instead, we're diving deep into Chapter 6 of our source material to understand the actual underlying mechanisms at play. The goal, to ensure your code is secured by design, and absolutely not just secure by accident.
So our focus today is public key encryption and digital signatures, unleashing RSA. We're going to completely demystify the core building blocks of modern application security. We'll be shifting away from just looking at complex abstract math and moving toward practical, day-to-day developer decision-making around public key cryptography. Honestly, when you buy products online, when you collaborate on a video call, or when you build distributed microservices, you are entirely depending on this specific technology. Without it, the internet as we know it today simply wouldn't exist.
Here is our roadmap for this explainer. We'll cover this in 5 parts. First, the developer security mindset. Second, the core cryptographic goals. Third, solving the key problem. Fourth, establishing digital trust. And finally, fifth, modern identity and authentication. This structure is going to guide us step by step.
Part 1. The developer security mindset.
To really get this right, we have to look at what we are actually trying to achieve when we implement security. There are 4 distinct goals of cryptography, and understanding them gives us a mental framework for knowing exactly when and how to use different algorithms. Let's make this super concrete. First, we have integrity. This ensures a hacker hasn't intercepted and modified your data in transit. For example, imagine changing a payment amount from $10 to $10,000 without anyone noticing. Integrity stops that. Next is authentication. This proves you are talking to the actual banking server you think you're talking to, and not a malicious, look-alike clone hosted halfway across the world. Third is confidentiality. This keeps prying eyes out of private data, ensuring that even if a database of, say, sensitive health records is stolen, the attacker just gets a bunch of useless, scrambled text. And finally, we have non-repudiation. This is a really critical one that we are going to focus heavily on later. It guarantees that a sender absolutely cannot deny sending a specific message. This is essential for things like financial transactions. A customer cannot call their bank later and claim, "Hey, I never authorized that $10,000 wire transfer." Proper cryptography gives us the absolute mathematical proof that they did.
Now, right at the heart of achieving that confidentiality goal is encryption. It is the process of transforming readable data, which we call plain text, into an unreadable form, known as ciphertext, using a key. It ensures that literally no one can understand your data without possessing the correct key to reverse that scrambling process. If you don't have the key, that ciphertext just looks like a random, completely meaningless sequence of bits. It's just noise.
Okay, moving on to Part 2, the core cryptographic goals. Let's see how these concepts build into actual operational mechanisms. We'll start with symmetric cryptography. In a standard symmetric cipher, the exact same secret key is used to both lock and unlock the data. It is very much like a physical key opening and closing a deadbolt on your front door. You take your clear text, feed it into the encryption algorithm alongside your secret key, and boom, it outputs the scrambled ciphertext. Then, the person on the receiving end takes that exact same secret key, runs the decryption algorithm against the ciphertext, and recovers the original clear text. The beauty of symmetric cryptography is that it is incredibly fast. It is highly computationally efficient, and it handles massive amounts of data with absolute ease.
But you might be wondering, what's the catch? Well, there's a massive vulnerability here, often called the fatal flaw of symmetric encryption. If you use the exact same key to lock and unlock, how do you securely share that secret key with a remote service in the first place without a hacker intercepting it? Historically, this was an absolute logistical nightmare. Think back to World War II, militaries literally had to distribute physical code books under armed guard, and if just one of those books was stolen, the entire operation was instantly compromised. Now let's fast forward to today's software development world. Imagine a modern cloud network running, say, 500 different microservices that all constantly need to talk to each other. Securely sharing a single secret master key across all of them is functionally impossible. And what happens if that single master key is compromised? Just picture being the developer who gets paged at 3 a.m., having to manually coordinate a secret key rotation across 500 disconnected systems simultaneously, all without causing a total network outage. It's a nightmare. The operational overhead makes pure symmetric cryptography completely unscalable for establishing distributed trust.
That brings us perfectly to Part 3, solving the key problem.
This historical secret key challenge is exactly what led to a revolutionary paradigm shift. Back in 1976, Whitfield Diffie and Martin Hellman introduced a concept that rendered the age-old reliance on secret courier systems completely obsolete. They introduced the concept of a key pair. This is a real game changer. You have a private key, which you guard with your life, and a public key, which you can safely and openly hand out to friends, enemies, and hackers alike. Instead of relying on one shared secret, these two keys are generated at the exact same time, and they are mathematically bound to each other. The real magic here is how they interact. The private key only works with this matching public key, and the public key only works with this matching private key. So if someone encrypts a message with your public key, only your carefully guarded private key can decrypt it. It acts a lot like a one-way drop box. Literally anyone can put a message into the box and lock it, but only the person holding the private key has the ability to open that box and actually read what's inside.
Let's apply this to that complex microservices architecture we talked about earlier. With this approach, every single service gets its own unique key pair. This completely eliminates the need to secretly share a single master key across your whole network. For example, your payment service, warehouse service, accounting service, and inventory service all generate their own unique key pairs. Then, they can freely and openly share their public keys with each other on an internal directory. There's no risk. If the accounting service wants to securely talk to inventory, it just grabs the inventory's public key to encrypt the message. Think about the blast radius here if something goes wrong. If a hacker manages to breach the warehouse service and actually steals its private key, they only compromise data that was explicitly sent to the warehouse. The communications between, say, accounting and inventory, those remain entirely secure because their private keys are completely isolated. Just like that, the secret key distribution problem is completely solved.
Now, the most famous system for doing this is RSA. It's named after its inventors, Rivest, Shamir, and Adelman. And it relies on a fascinating mathematical concept, the extreme difficulty of factoring the product of two massive prime numbers. Let's break down why this is so remarkably effective. In mathematics, multiplying two numbers together is computationally very, very easy. A computer can multiply two massive prime numbers in a fraction of a millisecond. However, taking that massive resulting product and trying to figure out which two original prime numbers were multiplied together to create it, that is incredibly hard. It acts as a one-way mathematical function. As long as those prime numbers are large enough, classical computers simply cannot factor the product fast enough to break the encryption. We're talking literally thousands of years needed to guess the original primes. Today, a 2048-bit key is considered a safe standard, though you'll often see 3072 or 4096-bit keys heavily recommended for long-term security. But there is a catch to all this mathematical elegance. Operating on these massive numbers is incredibly slow. It consumes a huge amount of computing power compared to those fast, symmetric algorithms we looked at earlier.
So, because RSA math is so heavy and slow, modern systems don't use it for everything. Instead, they use what's called hybrid encryption. This is where we combine the strengths of both systems. We use lightning-fast, symmetric AES encryption for the actual data payload, and then we use RSA just to securely lock up the AES key itself. You would never, ever want to encrypt a massive gigabyte video file directly with RSA. It would take forever and basically melt your server's CPU. Instead, we dynamically generate a tiny, temporary, symmetric AES key. We use that to encrypt the heavy payload at lightning speed, and then we use the slow RSA algorithm just to encrypt or wrap that tiny AES key.
Let's walk through the exact step-by-step life cycle of how this hybrid wrap and unwrap process works in a single request. It's a seamless team-up of AES for high performance and RSA for secure key distribution. First, a random key generator creates a completely fresh AES key. This is often called a content encryption key. Next, the fast AES encryptor takes this key and processes your large plaintext document, transforming it into ciphertext almost instantly. Meanwhile, the RSA encryptor takes that exact same AES key and locks it using the recipient's public key. The system then bundles this wrapped AES key together with the encrypted content and sends the whole package across the network. Now, on the receiving end, the process works in reverse. The recipient cannot decrypt the large document directly. First, they have to use their highly guarded private RSA key to unwrap the AES key. Once that AES key is successfully extracted, they use it to decrypt the bulk ciphertext and retrieve the original document. This brilliant architecture gives you the absolute best of both worlds. You get the speed of symmetric cryptography coupled with the secure key distribution of asymmetric cryptography.
All right, let's move on to part 4, establishing digital trust. Because setting up public keys is only half the battle.
We have to ask a really critical question here. If public keys are being sent freely over an open network, how do you actually know the key you just received belongs to your payment service and not some imposter? Yes, public keys are meant to be public, and distributing them doesn't expose your private data. But cryptography alone doesn't solve the problem of identity. If a malicious actor intercepts your request for a key and simply hands you their own public key instead, you've got a massive problem on your hands.
This is exactly what happens in a classic man-in-the-middle attack. Picture this. The client asks the server for a public key, but an attacker intercepts the communication. The attacker grabs the real key from the server, but maliciously forwards their own public key down to the client. The client, who is completely unaware, encrypts highly sensitive data, like credit card numbers, using the attacker's key. The attacker then decrypts it, reads all the private data, re-encrypts it with the server's real key, and passes it along. The transaction succeeds, and nobody even knows they are being watched. So how do we stop this? To prevent it, public keys must be bundled into X509 digital certificates. Think of an X509 certificate as a tamper-proof digital passport. It contains the public key, sure, but it also contains verified identity information about exactly who owns that key. Crucially, this certificate is digitally signed by a certificate authority, or CA. A CA is a highly trusted third party, companies like DigiCert or Let's Encrypt. Your operating system and web browser actually come preloaded with a list of CAs that they inherently trust. When your application receives a public key, it doesn't just blindly accept it anymore. It checks the X509 certificate, verifies the certificate authority's signature, and absolutely confirms that the entity handing you the key is exactly who they claim to be. This entire system is known as Public Key Infrastructure, or PKI, and it is the invisible shield that stops man-in-the-middle attacks dead in their tracks.
Now, beyond just encryption, RSA also gives us the power of digital signatures. This is where a service signs a payload with its private key, acting as an unforgeable digital seal that anyone can verify using the public key. For digital signatures, the roles of the keys are entirely reversed. Remember, for encryption, use the public key to lock and the private key to unlock. But for signatures, you aren't trying to hide the data, you want to prove its origin. So a service hashes the data and then encrypts that hash using its own private key. Because only that specific service possesses its private key, the resulting signature acts as absolute proof of origin. It is a cryptographic guarantee that the data hasn't been tampered with. The receiving service then just uses the widely available public key to decrypt the signature and verify that the seal hasn't been broken.
This brings us to a crucial point about trust. Unlike HMACs, which share a secret, RSA signatures provide true non-repudiation. Why? Because absolutely no one else possesses the private key required to forge that signature. With an HMAC, because both the sender and receiver hold the exact same shared secret key, technically either one of them could have generated the specific code. You can't prove to a third-party auditor or, say, a judge in a court of law who actually created the message. But with an RSA digital signature, there is zero doubt. If the signature successfully verifies against the public key, it mathematically had to come from the sole owner of the private key. This creates a legally and financially binding audit trail.
And that takes us to our final section, Part 5, Modern Identity and Authentication. Let's see how this all builds into the applications you develop and interact with every day.
In a real-world scenario, like microservices processing refunds, configuring a 2048-bit or higher RSA key ensures you are adhering strictly to zero-trust principles. Let's say a warehouse employee approves a refund. The warehouse service takes the JSON file containing those refund details and encrypts it using the payment service's public key. But as a developer, you have a critical decision to make here regarding something called padding. Historically, systems used an older padding scheme known as PKCS1 version 1.5. However, this older standard turned out to be highly vulnerable to what are known as Blankenbacher attacks. In a Blankenbacher attack, a hacker repeatedly sends slightly modified ciphertext to a server and carefully monitors the exact error messages the server returns. By observing whether the decryption failed due to bad formatting or bad padding, the attacker can actually systematically deduce the underlying private key over time without ever actually stealing it directly. To prevent this, modern secure systems absolutely must use RSA OEAP padding. OEAP stands for Optimal Asymmetric Encryption Padding.
What it does is add randomized data to the plaintext before the encryption even happens. This ensures that even if you encrypt the exact same JSON file twice, the resulting ciphertext will look completely different every single time. It completely neutralizes the Blankenbacher vulnerability.
While RSA undeniably remains an industry standard, we have to talk about the ongoing cryptographic evolution. There's a major shift right now toward elliptic curve cryptography, or ECC. ECC uses entirely different math to offer the exact same level of security, but it acts like a high-performance sports car with a fraction of the key size. Think of RSA like a vintage station wagon. It's reliable, it's battle-tested, but it's really heavy. Because it relies on prime factorization, the keys must be massive to stay ahead of modern, powerful computers. Elliptic curve cryptography, on the other hand, relies on the algebraic structure of elliptic curves over finite fields. A tiny 256-bit ECC key provides the exact same cryptographic strength as a massive 3072-bit RSA key. This results in a huge reduction in battery drain, bandwidth usage, and compute costs. As you can imagine, this is incredibly critical for modern mobile devices and high-scale cloud architectures where efficiency is everything.
Whether you use RSA or ECC, these cryptographic signatures are ultimately what power modern, phishing-proof authentication like WebAuthn. This is where your hardware key physically signs a login challenge using an unstealable private key. Here's how it works. When a user tries to log in, the application server generates a random string of data called a challenge value and sends it to the user's browser. The user's hardware security key then uses its embedded private key, which is literally burned into the silicon and cannot be extracted from the device, to digitally sign that challenge. The server then just verifies the signature with the user's registered public key. But here is the real magic that makes it phishing-proof. The signature process is cryptographically bound to the specific domain you are visiting. So even if you are tricked into visiting a fake lookalike phishing site, the hardware key recognizes the domain mismatch. It sees that the domain doesn't match the one it originally registered with, and it simply refuses to sign the request. The attacker gets absolutely nothing.
Now that you understand the powerful math and the operational mechanisms hiding behind the black box of security, I want to leave you with a challenge. Look at your own code. Ask yourself, are you building trust deliberately? Are your applications secure by design or just secure by accident? Whether you choose RSA for its legacy compatibility or ECC for its sleek performance, whether you are encrypting heavy payloads with hybrid techniques or generating undeniable digital signatures, you are now equipped to make informed architectural decisions. You know why key pairs solve the massive distribution problem. You know why OEEP padding protects against advanced attacks. And you know why X.509 digital certificates are absolutely non-negotiable for establishing identity. So get out there, inspect those key sizes, audit your padding schemes, and start building software that is undeniable, purposefully secure by design. Thanks for joining me on this explainer.